Okay, everybody, thanks for hanging on a minute there. So the first thing to note today is just a practicality. As you know, I occasionally have not put up the PDFs before the lectures, so just to let you know that the PDF is live, but just for convenience, I've put it in the home page, okay? So if you go to the home page, just for now, you'll see the PDF for this current lecture, okay? If you need to follow along in Canvas. As regards the test yesterday, thank you for your patience. Some of you, because I know there were some issues, particularly in the first session. The good side of that is it means we've now ironed out, hopefully, all the kinks and all the unexpected features that Canvas has to offer us. So hopefully it will be more straightforward next time. We will make every effort to make sure that the grades that you receive from that first assessment will be fair and that there'll be options available to people who had any issues there that they're not happy about, okay? So at this point in the course, probably some of you feel as if, well, we've had a lot of information thrown at us recently, and so usually I take an opportunity to just take stock before we zoom on. Now, what we've been doing over the last week or so of lectures is we've been laying the foundations for state machines, okay? Now, there is a slight disparity in background of students on this course. So some students come from XJTLU, and in XJTLU, you've had 2 years of digital logic, so you may have been familiar with a lot of the concepts that we've been discussing. Some of you come from the first year on the Liverpool campus, and for you, you've seen some of the concepts, but you actually have, you have quite a breadth of coverage in the first year without necessarily knowing quite how each topic fits in. So that's one reason why we spend quite a lot of time in the first couple of weeks introducing you to combinational logic concepts and introducing you to sequential logic, that is, the likes of flip-flops, latches, etc. Okay? Now, at the same time, because of that, then there's been a lot of material covered. So today, we're actually going to look at these things, but one of them, actually, I've reserved for the asynchronous video because it will slow us down. So we're going to look at these 4 topics, but you'll see that they're all closely interconnected, okay? And this is what we've been building towards. This is some of the previous material that we've covered. And there will be, as I said yesterday, when I get half a minute, there'll be a couple of asynchronous lecture videos uploaded to Canvas to just unpack, for example, what we did with counter design. But at this point, it's important to just re-emphasize, and I do say this a lot in the first half of the course. We're now moving really, or we're moving to the second half of our digital content now. But I do say this a lot, and I'll say it again. Please, if you feel like a topic hasn't been covered well enough, just look back first at your notes from ELEC143, because often we are building on material there. So, for example, what I looked at yesterday, and I kind of skated over, was counter design. Actually, you cover counter design in ELEC143, okay, unless it's changed radically in the last year. And while there will be some short asynchronous videos just to help you kind of unpack exactly how you go through the steps of making the next state maps, etc., actually, that topic is something you should have been familiar with already. So I'll do everything I can to support, but we do have now to move on to, if you like, the main meat of this module, the main material. So just give you a graphic about the journey that we've been on so far, sometimes at whistle-stop speed. We've started with revision of logic gates, combinational logic. We moved on to combining these to make slightly higher level devices like multiplexers, decoders, read-only memory, programmable logic array, programmable array logic. Okay, and these are known as programmable logic devices, right? Then we moved more recently into latches last week and concepts of timing and memory and realizing the importance of sequential logic when things are happening in a sequence rather than just the logic just happening all at once, as we assume for combinational logic. And we looked at the possibility of glitches, that is unexpected output due to this sequence and the time involved. And we looked at how to analyze things with timing diagrams. We extended this into flip-flops. Okay, so latches, what's the difference with a flip-flop in terms of how we use them? Well, the difference is that a latch is not able to prevent all glitches, whereas a flip-flop is synchronized by the clock. So it's not just sequential, it's not just a device that accounts for a sequential signal taking time. It's actually synchronized. So a synchronized swimmers, everyone does everything at the same time, right? So synchronized by the clock, everything's controlled and monitored by that tick of the clock. Now that clock is actually happening very quickly, maybe 50 megahertz or 20 megahertz, but we slow it right down in our minds and our diagrams because we know that each tiny nanoseconds matters. We then looked just yesterday at creating registers of flip-flops. So it just means a bunch of flip-flops that operate together, okay, and they're all common, have a common clock that synchronizes their operation so that we can deal with words, digital words like 0110, okay? So collections of bits, maybe a byte. And we looked at the concept briefly of output and feedback, and we also introduced some more complex devices made of all these early devices. And we thought a bit about lookup tables, okay, which is how FPGAs are usually built. And they basically implement a truth table. So again, just finishing looking back, we've also started to consider, when we looked at counter design yesterday, we started to think about how we can put together combinational and sequential logic so that they work together to create actually a state machine, which is what we're moving to today. Okay, and we're going to define what a state machine is and look at how it works in a bit more detail. We looked at how to depict this. We didn't actually look at a state graph, but we looked at an action table, and I said it's pretty similar to a state graph. And we looked at how to work out next state logic. And we did an example, but we were rushing, so I said that I would put up, as I say, that asynchronous video just to help you, if you want to unpack how you work out the nuts and bolts of the logic for the next input of the flip-flop, okay? So what we're coming to today is this design of state machines, okay, with both combinational and sequential inputs and also with outputs, okay? And let's begin. So what's the difference between combinational and sequential and synchronous? Well, here we have a combinational circuit on the left. And in this case, we can see that the inputs, we can almost say that the effect on the output is immediately. So I've put that in quotation marks because it's not quite immediately. There's a short propagation delay, right? But let's say we have two inputs to this circuit here. When I say immediately, and it's not immediately, it's within, a couple of nanoseconds, let's say, but it's just the time that it takes for the signal to travel through the gates, down the wires, and then be monitored as output. So we can see here that this is an output of the circuit if the signal is traveling from left to right, which you would usually assume, unless you're told otherwise, on a diagram of this type. So we have a combinational output. Z is not A I0 plus A I1. Okay. So that's pretty straightforward, but it all happens in pretty much real time. And there's not really a concept of state here. We just have kind of a continuous stream of outputs. So if we changed the value of these inputs, let's say I0 starts off being worth 1, but then later it changes to 0, well, that change will change almost immediately the value of the output, right, after a short propagation delay of the signal traveling through the circuit. So we don't really have such a thing as a state, and we don't really have a concept of sequence of the signals. I mean, there is some sequence there as the signal travels through, but there isn't any synchronization of that sequence, and there's no memory. So we just have present inputs affecting present outputs. But when we come to sequential and particularly synchronous, that is clocked circuits with a common clock, then we immediately have a concept with these sequential devices of state, okay? Because these flip-flops here, this register of flip-flops, these are sequential devices. These are the building blocks of our sequential and synchronous circuits. And you can see what I meant about a common clock. They're all synchronized by this same clock. Okay, so it's a bit like a heartbeat of the circuit, determining what's happening at each stage. And we have a present state of these and the next state. Now, I've just added these lines. To show what I showed you yesterday. So you may recognize this circuit as one of the counters from yesterday. And I kind of started to show you in pen where, you know, the actual lines might be here. It was kind of assumed that if we have not be here, then it must be connected to the not be output here, right? But I've just filled them in here. And what you can see about this circuit is that it's got a present state that is collectively, what are the Q outputs of the flip-flops? And we can see there's 3 outputs here, C, B, and A. And collectively, we could say CB8 equals 0, 1, 0. All right, that's the present state of the system. But the next state, when we're dealing with D-type flip-flops, is simply, what is the data input waiting to be loaded onto each flip-flop? So we call it D subscript C, if it's the data input for C, right? D subscript B and D subscript A. These are waiting to be loaded, okay? So these are known as the next state. Intuitively, you might think left to right if you've got an English background. So you might think, oh, this would be the present state and this would be the next state. But don't fall into that trap. This is the present state. This is what's currently showing on the flip-flops. Now, this circuit as well is a bit insular. I don't mean that in an electrical sense. I mean it in the sense that it hasn't actually got any genuine bona fide outputs and inputs, right, that are external to the circuit. So at the moment, we just have the states, the present state and the next state, but we haven't got anything external. This is a closed loop, isn't it? There's nothing external coming in as an input. It's just taking its own present state and using that with some combinational logic to determine its next state, okay? So what we need to do if we want to use this circuit is we need to insert some circuitry for outputs and inputs, okay? So external outputs to the circuit and test inputs where, you know, in a simple way of thinking, the user could press a button and could change the behavior of the circuit, okay? Otherwise, it'll just be an endless loop cycling through, not telling anyone what its output is and not able to change in response to any input. So what would be logical here would be, if you remember the 7-segment decoder circuit, where we could then hook something up so that we get a binary input and we'd output a 7-segment display. Well, if this is a counter, I can't remember which counter this is, but let's say it's cycling through from 0, 0, 0 to 0, 0, 1 to 0, 0, 0, 1, 0, 0, 1, 1, and so on, then what would be nice is to connect up some 7-segment decoder circuitry so we could display what's happening here on a screen in decimal. Okay, so that it would cycle through 0, 1, 2, 3, 4, 5, and so on. But here I'll just show you a more simple example where, let's say we have C, and this is completely random. This is not to do any kind of 7-segment display, but we might altogether the outputs C and B, and hey presto, we have an output which is C or B. And suddenly this circuit has a genuine output. Input, similarly, we could, again, just completely randomly add some input. Let's call this, notice how the one on the left has I0 and I1. Well, I'll call this I0 and just say, you know, this is a user input where the user can influence the behavior of this circuit by changing the value of I0, okay? So suddenly now this circuit has some inputs and outputs as well as its present state and its next state. And all these 4 things need to show up on anything that we do to depict this circuit, so any analysis. Yes?
So is the present and the next state sort of like the action the circuit takes?
Not quite the action, but it's like the situation of the circuit, if you like. It defines where the circuit's at the moment. And we can choose what elements of that we then output as outputs that we can read. Yeah?
Just because it has an output, it doesn't actually give like a reading on what its state is?
Exactly right, yeah, because there could be some combinational logic there like this that is masking what the real state is, or omitting some of it, yeah. Any other questions? Okay, so let's now move to, now that we've inserted some, fake or relatively meaningless inputs and outputs to this circuit, let's have a think about the types of inputs that we can have, and we're going to come back to this later in the lecture, but some inputs can influence output directly or immediately, but this only happens in certain types of circuit, whereas other inputs must wait for the next active clock edge, okay? Now, what on earth does that mean? Well, it's actually very simple. This input here, I0, has to wait. I better stop hovering over that or we'll get a dodgy video. This input here has to wait for the clock, right, to have any effect on the output, because these flip-flops here are very well disciplined and they're all controlled by the clock. So even though this input here will have an almost immediate effect on the data input to this flip-flop, it's not going to have any effect on B itself until the next tick of the clock, when that suddenly all gets loaded, okay? So how can we create a circuit? Well, that type of circuit is called a Moore circuit, when the inputs have to wait for the clock edge to affect the output, okay? But we could have a system where, let's say, we really want the input to have a direct, immediate effect on the output, and we call that a Mealy circuit if we have that. What if we did this? Then suddenly, we're cutting the flip-flops out of the loop. That register of flip-flops is being cut out of the loop so that I0 can now have an immediate effect. Not quite immediate, I'm using it in this slightly vague sense. It's going to take a couple of nanoseconds or whatever to travel down the wire, probably less than that. But here, it can have a semi-immediate effect on Z. We say it can have a combinational effect, because combinational logic doesn't need to wait for the clock, right? It's just in real time. And that suddenly means that Z might fluctuate. If we change I0 now from 0 to 1, it's going to have an almost immediate effect on the value of Z potentially, okay? Because Z is ORing together I0, B, and C. So let's say C and B were at 0, and Z was 0, but then if we change I0 to 1, suddenly Z becomes 1, and so it might fluctuate. So we take a risk if we do that as well, right? Because we could get fluctuations in the output. We're going to explore that a little bit, but the main driver, in the way we think of state machines, of current output is the present state, okay? So we've seen here that we can have another driver, which in a Mealy circuit, what we call a Mealy circuit, we can have the input having some direct effect on the output. But the main setup of the way that we design state machines is to have this kind of clocking and controlling everything, so that the main driver of the current output is the present state. And sometimes we also allow inputs to have a direct effect. Are there any more questions on that? Because there's really some crucial concepts, yeah.
So if the output of DB is low and I/O is high, what happens to the input of?
So when you say the output of DB, do you mean really this state here? So this present state of flip-flop B is high and I0 is low. Well, because we've got an OR gate here. I've not drawn that very well, actually, because I've just connected them both to the same line. I've just realized in my rush. So I can see your confusion. Let's just draw it a bit better. So that's how not to do it, right? So we had B here, and let's say that B. What else should we do? Why would I lose a mark on this slide at the moment in an exam? Can anyone tell me?
You input the dots.
Yeah, so there's no way of knowing if this is a junction or this is a junction, etc. So put a node at least, or put a bridge there at the other place if you need to, if you prefer to do that. Okay, so now I could draw this in a bit better and do this, right? If if I can do it without clashing. Does that make a bit more sense now? Okay, so all I was saying before is that, you know, if these two are 0, this and this is 0, then the OR gate's going to output 0, but if we change I0 to 1, then it's going to have an immediate effect without waiting for the next tick of the clock, which in a digital logic perspective, the next tick of the clock might only be 5 nanoseconds away, but in digital logic, that could be a long time. Okay, so rather than waiting for that, if this is directly connected to the output, then this signal can have an immediate or semi-immediate effect, yeah.
Why would you want that?
Well, we'll find out, but it's a good question, yeah. Why would you want that? And sometimes you want to have more direct control on the clock office, okay? One option might be, for example, for a reset, okay? Right, any more questions? Okay, so, forgot just one part of this slide. So we've got a feedback loop here, right, in the circuit, and we usually do. We have some kind of feedback from the present state to influence the next state, but we also need our outputs and inputs, okay? So just jumping back, again, we're slightly reflecting today to try and draw everything together for state machines. Remember that turnstile in lecture 0? So we had that situation which at the time you probably thought, what on earth is Dr. McIntosh talking about? So you may begin during this lecture to understand a bit more what I was referring to. It's a very everyday example of a turnstile where you have to put a coin in to make it operate, okay? And it won't open unless you put the coin in. So we could envisage 2 states which maybe we can control using digital logic, where in this first state, it remains locked until you enter the coin. Well, entering the coin is a bit like an input, okay? So that's a bit like an external input to the circuit, which changes the behavior of the circuit. So while it's locked, we can't make it move to an unlocked state except with the correct input, the coin. So we insert the coin and it becomes unlocked. But then it doesn't, we haven't actually pushed it yet, it's just unlocked, right? And we're standing there, we've put in our coin. It doesn't matter how many more coins I put in, it's not going to make it go back to being locked or going to make it any less unlocked, right? It's going to remain unlocked. As soon as I put that coin in, as soon as I put that coin in, it becomes unlocked. What I need to do now is to push. So then, again, that's another external input to the circuit, to push it and make it locked. Now, that's in a real-world context, but it just might give you a sense of why we design state machines in the digital world the way that we do, okay? Now, another example of a state machine, that was a very simple state machine, that turnstile. Another example is traffic lights, okay? So we could take a very simplistic view and say, well, there's 4 possible states, okay? Now, in this case, what we've done is we've kind of made the states, a bit like with our counter, we've almost, in our example yesterday, we almost made the states as if they were the outputs. These are really the outputs of the circuit. And you usually find that the outputs go inside the bubbles on what's called a state graph, which is what this is. So here's our various outputs. But if we were going to be a bit more rigorous about this, we'd say, well, let's call this state 1. And then let's also remember, well, it doesn't want to just stay on red for a couple of nanoseconds. It needs to stay on red maybe for a good period of time. So we might insert a few extra bits and pieces, a few extra states. And maybe we'd insert, 100 extra states in which the output is red, okay? And I'm only inserting 2 here, but you see the idea. And we have state 2, state 3. And the really important thing to note is that in between each of these states is 1 tick of the clock, okay? So this is a state graph, really, okay? It's a very simplified one, but in between each of these states, we have 1 tick of the clock, okay? So which is why I said, you might need to insert several states, or you might need to insert a loop where, depending on the input, this state just keeps going back around to itself, okay? But this is, again, just another real-world example of what is actually a state machine. It's a machine built of several states, okay? And those states have outputs associated, and we could modify this to include inputs. What could be an input at a set of traffic lights? Yeah? Right, so if it has some kind of detection of whether a car's approaching to tell it to change to green, the car's going too fast, tell it to change to red, or if a pedestrian presses the button on the crossing, tell it to change to red. So we have several states here, and obviously, you know, as I said, this is a simplified diagram, but just in case you were wondering, you know, we would continue this and we would put, but there's actually rules, and we'll look at them in another lecture, of exactly where you put these state names, okay, and where you put the outputs and where you put the inputs on a state graph, okay. So we've been building up to what is a state machine. Well, for those of you who are more theoretically minded and trying to kind of marry this up with other concepts, well, it's fundamentally an abstract concept, right? It's a name that we use for a machine that has a sequence of states and has inputs and outputs, right? It's any device which stores information about its status or state, and it has memory because it needs to have memory to be able to store that information, and it has the possibility of inputs and outputs, as I've just said. Sometimes it's called a finite state machine, okay? It just means that it's a state machine that has a limited number of states, right? It's not infinite, okay? You could argue that all state machines are finite. I guess it depends whether you see the universe itself as a state machine and whether you would see that as infinite or finite, but that's just a philosophical, probably irrelevance for most of you. So we use state machines to model the design of digital hardware, right? So transitions from state to state are triggered by inputs and present states. Output is triggered by the state and or directly by inputs. This is really stuff we've already said, right? So we're saying input can affect how we move from one state of the machine to the next, but it can also sometimes, if we design it so, have a direct effect on the output. Okay? And we've talked about Moore and Mealy machines, and we're going to look at them now, but just here's some examples of state machines. You know, we already looked at traffic lights. We have here something else, some kind of board. I think it's the core for an i7. And here we have vending machine, okay? So, sorry, the CPU for a Core i7. So, another definition there. But what we talk about with Moore and Mealy, okay? So, in the Moore model, the present output is a function only of this present state. What does this mean? Well, before you look at this slide, just try and keep it simple, because one of the issues we have in digital logic is that, and as in any academic discipline, people come up with quite technical definitions for things. The reason for that is because we need to be rigorous, right? So we need to have an exact, precise definition of what we mean by a certain thing. But in practice, often the meanings are quite simple. Okay, so the biggest barrier to learning a new topic is usually the terminology. Once you've understood the terminology and got a way that works for you, then everything else follows. You do need to be aware of the technical terminology, but this Moore machine is none other than the kind of circuit we had here before we added this line, right? So a Moore machine is just something where the input can't directly influence the output, okay? A Mealy machine is one where it can. That's it, okay? But you need to be aware of and able to recite or reproduce in some technical form the technical definition. So let's just spare a few minutes to have a look at the technical definitions, all right? Another way of saying what we just said, in the Moore model, the present output, that is the current output, is only a function of the present state. So the only thing that can affect that current output is that present state, right? The only thing that could affect Z in the Moore model, if we didn't have this line, would be C, B, and A. Okay? Whereas in a Mealy model, the present output is a function of both the present state and the present input, okay? So that extra line that we added on our diagram can have a direct effect or semi-direct effect on the output without waiting for the clock, and that was indicated here. So that's the Mealy model. We can have a direct line to the output, okay? So these definitions at the top are important ones that I suggest you pretty much memorize, okay? Just in case you come across them, yes?
So the coin machine would be Mealy and the stoplight would be Moore?
Yeah, so the coin machine really, they probably don't work like that. The coin machine, I would say, could even be a Moore machine, because actually all the coin was doing was affecting the next state of the system. But it's not a perfect analogy, right? Because we then had to push it, so it wasn't really waiting for the clock to do anything. So it is really not a proper state machine, that coin machine. But yeah, good question. Okay, so if we now look here, and I'd invite you to look later, because I don't want to bore the socks off you, we can see some kind of discussion of what this means, but I just want to highlight something from both of these slides to you, the Moore and the Mealy. What have they got in common? They've got some combinational logic, they've got some sequential logic, which is the beating heart of the system, that's your flip-flops, okay, and they've got some other combinational logic. What are these two doing? Well, this one is a block that is working out the next state of the system, and we might have an external input plus a connection with the outputs of the, and I'm using the term output loosely, with the states really, the present states of the system. Where's this on our previous diagram? Well, it's here, right? This is the next state combinational logic, all right? But we also have some output combinational logic. Well, this is taking the present states of the system, maybe the values of those flip-flops, A, B, and C, not maybe, actually the values of those flip-flops, okay? And it's doing something with them, combinationally, putting some gates in, or maybe putting in a programmable logic device to determine what the outputs are going to be. Where's this on our previous diagram? Well, it's here, okay? This is a very simple output combinational logic. So, some students, I would be almost certain, would look at something like this and a slide like this and think, oh man, that looks a bit off-putting. Try and just relate it step by step to something that's familiar, and that way you usually can figure out what it's talking about. Others of you may find it really helpful to have a kind of overview. Okay, I've put those kind of less formal definitions at the bottom and the right, but you need to be aware of these and be able to quote these definitions at the top, okay, of each of these two slides, and understand what they mean in practice. Right, we could summarize this even more formally, but when I say even more formally, I mean mathematically. Again, some of you may look at this and think, but that's fine, because it's not essential to your understanding. However, I would invite you to take a look at this. What we're basically saying here is, in all cases, the next state is some function, some combinational logic function of the present state and the present input. In a Moore machine, the output is only a function of the present state. In a Mealy machine, the output is a function of the present state and the current input. Okay? So I often use this word present from now on. Okay? Present and current in this context just mean what's happening now, right? So the present state is the state of the system now, okay? As opposed to the next state, which is the state of the system after another tick of the clock, when the next state logic then gets transferred to become the present state again, okay? So the next state would be what's waiting. It's not to be transferred onto the present state. Okay, so a lot of theory there just to set the stage, and some relation to real life. Any questions at this point? Okay. So, this is another example of a more sequential circuit. The output only changes when the state changes. So here what we've done is very similar to our diagram that we kind of opened the session with, but this time we've put our flip-flops on one side, right? So the signal here, I mean, how would you even begin to approach a diagram like this? Because the first time you see it, you're probably thinking, well, what do A, B, D, X, and Z mean? Which one's which? What do they represent on the circuit? Well, the place to start is look at the flip-flops, right? And you can immediately see that A and B must be the present states of the flip-flops, okay? And sometimes it can be helpful to even draw a dividing line across the middle of the flip-flops to show the divide between the present state and the next state. So here at the top here, whereas it was on the right before, we have the present state. here we have the next state of each flip-flop waiting to be loaded at the next tick of the clock to become the new state of that flip-flop. Okay, so state really now refers to the value of Q on each flip-flop. In this case, we've labeled Q to be A. In this case, we've labeled Q to be B. Right? Remember, Q was kind of like one of the outputs of the flip-flop, and not Q was the opposite, okay, the inverse. So here, we can immediately tell, well, these must be the present states, A and B. Well, that tells us, we can see the direction of the signal flow here. It must go from D subscript A to A, right? And D subscript B to B. So that tells us the direction of flow in this circuit. And if we know the direction of flow, then we know that this Z must be the output, right? Okay? So that must be the output. And that only leaves us to figure out the difference between X and A and B down at the bottom. Well, clearly, we already know what A and B are. So this is our feedback loop, or our two feedback loops from A and B to affect the next states. This is our next state logic, right? So if A and B are the states of the flip-flops, then X must be the external input. It's just coming from nowhere, isn't it? So this must be the input. We'll just put IP, okay? So that's pretty important to be able to do that skill of being able to kind of look at a circuit and figure out what are the present states, what are the next states, what letter represents the output, what letter represents the input. Maybe there's multiple outputs and inputs, okay? And we have our next state combinational logic and our output combinational logic, okay? Now, how do we know that this is a Moore circuit? Well, the present state is only a function of the present output here is only a function of the present state. But you might say, well, it is a function of X, because look, X is affecting the output, but X isn't immediately affecting the output, right? It still has to basically affect the state first, and after it's affected the state, that'll have a knock-on effect to the output. There's no direct line from X to Z here, or even from X to some combinational logic, and then to Z, right? Whereas in this case, slightly convoluted case here, I hope you can see that X has a direct line, okay? So here now, X not only affects the flip-flop next states and then present states and then output, it also has a direct line to this combinational logic. And so fluctuations in X, or changes in the value of this X input, can directly affect the output Z, okay? Now, there will be two mini videos which I've picked out, which I think are useful to you, where, again, rather than me spending ages here going through tracing circuits through a system, a skill that you need is signal tracing. Okay, so you need to know how to use signal tracing and to be able to construct a timing chart from it. We've looked at that already a little bit in week 2, but I want you to have a look at the asynchronous videos. They're short. I think each one is about 9 minutes, okay? And they'll show you how to take a circuit like this or this, trace the signal through it, and so that if you're told what the sequence of inputs is, for example, you can map out what the output should be, okay? You'd also need to be told the starting values of A and B. So let's finish by just looking at a bit of terminology and how we analyze state machines. So we mentioned before state tables and graphs, and these give us a really systematic approach. Okay, and it can actually help us both in analysis and in synthesis, which is essentially, if we think of it loosely, it's just how you build a circuit, right? How do you go about starting to, you have some logic that you want to implement for a particular thing, maybe a game, and how do you take that and translate it into a logic circuit, which is a state machine, okay? So let's look at this example where we have, at the moment, we're doing a bit of analysis, really. So we have this state machine here, and it's one that I think we already looked at just a couple of slides ago. And we're given this information, AB equals 0, 0, so that means both A and B are both 0, and we're also told that the initial input is 0. So we need to be able to work out what X is, what Z is, rather, in that case. So what we can do, and I'd invite you to look at the mini videos on signal tracing, but we can take, basically, if we say, okay, A is 0, therefore we have a 0 here. We know that X starts as 0, so we have a 0 here. If B is 0 to begin with, this is just initial information we've been given, then not B must be 1. Okay, we know that X is 0 to start with. Using this initial information, we can, well, 0 exclusive or 1 must give a 1 here. So this is going to be the next state of A after the tick of the clock. And 0 or 0 is going to give 0. And so we know initially that here we're going to get 1 exclusive or 0, but only after the tick of the clock. So because we were told that initially the present state of A and B is 0 and 0, if we exclusive OR together 0 and 0, then we know that initially the value of Z is 0. Okay? And we know the next state, so this is A plus B plus, which is the same on a D-type flip-flop as saying the inputs of the flip-flops, D subscript A and D subscript B, they're going to become the next states. So after the tick of the clock, AB is going to be 1, 0. So we can say the next states of AB are 1, 0. So there's more about that in the video so that you can pause and understand how to analyze. But what I'm kind of telling you is that that allows us to start building a state table. Okay? And a state table is showing the present states. So on this first row, we have AB equals 0, 0. And we've just organized this in binary order, 0, 0, 0, 1, 1, 0, 1, 1. We've created all the possible states of A, just like on a truth table, that we would do with the inputs on a truth table, or we do that with the states on a state table. And so then we start analyzing and saying, well, if AB equals 0, 0, but X is also 0, what would the output be? And the output would be 0. We worked that out here. But also, what would be the next states of A and B? Well, we know that A plus B plus would be 1, 0. So we put that here. Then we try it. What if X, the input, was equal to 1? What would the next state be then? Okay? And we can fill out a state table, okay, which is essentially, as I say, like a truth table, but with states in mind, and also considering inputs and outputs. Okay, so here's our input X and our output Z. Next states and present states. And usually you'd label it to show that. So here, what we could have done is we could start, a bit like that traffic light example, we could start to label up our states. So we could say, when A is 1 and B is 0, we regard that as state 3. When A is 0 and B is 0, we regard that as state 0. Okay? And when A is 0 and B is 1, we regard that as state 1, and so on. So we could substitute that and just simplify our state table a bit if we wanted. Okay? When we start to move away from talking about the flip-flop values here, the states of the individual flip-flops, then in this course, our convention is that we start talking about this as just a state table. Whereas when we have the flip-flop values as well, and we have everything properly labeled, we might refer to this as a state transition table. It's just a matter of convention. There's lots of different conventions that you'll find online. The really important thing here is that both of these are state tables, okay, in different forms. Now, a state graph we talked about before in the traffic light example, but here's a more formal example, okay? If we have a Moore machine, I said before on the traffic lights, we put the outputs inside the bubbles, right? Okay, but we also I was putting the state names up here, okay? But that was a bit sloppy, really. In a real state graph, you need to put the state names inside as well. So to distinguish them, we're going to put a line between. So here's the state name at the top, and here's the present output of that state, okay? These are our inputs. And what we're saying is, if the input is 1 at that tick of the clock, then on the next tick of the clock is going to cause us to move to state 1, okay? If the input is 0 while we're in state 0, then on the next tick of the clock, we're going to move to state 3. And so we start to describe some more complicated behavior of our state machine, okay? That the influence of the input, not on the output, because it's a Moore machine, so there's no direct influence on the output, but it can have an influence on each tick of the clock on what the next state is going to be. Sometimes, if an input is a given value, like here, if we're in state 2 and the circuit input is 1, the test input to that circuit, it's just going to cause us to cycle around and go back to that same state. A bit like maybe those red traffic lights, maybe when the input is 0, let's say, the input being defined as there's no car being detected and no one's pressed the button on the traffic light, then its default is maybe to remain in a green state and just continue cycling back round, okay? Now, there's a question that we're going to deal with in one of the problem classes next week. And I just want to check there's nothing else super important here before we finish. I think this will be a good stopping point. So this is the last slide here. A state graph of a Mealy machine is slightly different. I'd invite you to have a look at the differences, but I can summarize for you. The key differences are, look here, we don't have the output inside the circles. In a Mealy machine, the present input can cause the output to fluctuate. So the output is not fixed for a given state, right? It's a really important concept. The output here, we can't say what the output is in state 0 because the output could be affected by someone pressing that input button and changing it almost immediately, all right? So what we do is we write the input and the associated output together instead of the state and the output together. So here's the input and the associated output and the effect on the next state. Input of 1 causes a semi-immediate output of 1 when we're in state 0, but also causes us to cycle through to state 1. Okay, I hope that we've set the scene okay for state machines. Thank you for your attention. I will put up the various things I promised, and we'll have a problem class this afternoon to back up and kind of cover some of the material from section 3. Okay, thank you guys.